Okay. So what we are going to be doing for today is we are continuing on with trig substitutions. So let's see. Here we go. And so what we're going to be doing, this is going to look very similar to one of the last sections that we did from chapter 7, because you're going to recognize those square roots. They look very similar to what we've done before. And actually, I want you to be keeping that in mind while we are answering these questions. So the first thing, we've talked a little bit about this, but I just wanted to remind all of you of these two integrals, because I know that we had one, I think there was an arc length question on one of our past tests in term 2 where you had to integrate secant, and it ended up turning into this. And one thing that I've used to help myself remember is that I know that the derivative of secant is secant tangent. And I notice up here that when we integrate secant, we still end up with a secant tangent. It's just that the difference here is that we are going to be adding them together rather than multiplying. So that has been one way that I've been able to remember the antiderivative for secant. And then cosecant is similar because I've remembered the derivative for cosecant is negative cosecant cotangent. And likewise, then up here, you can see instead of multiplying, we've got cosecant plus cotangent. We still do have the negative, though, in front, so we can still remember that. So that was the first thing. Then getting into these trig substitutions. So I was supposed to be hiding this part here. Obviously, I forgot. But pretty much what I was hoping was that when you looked at this, that right there should have looked very similar to when we were doing our antiderivatives into the inverse trig functions. And so what we're going to do is we are going to make a substitution. So this here, remember, u represents whatever our function is in terms of x. And so we are going to start with this substitution, u equals a sine theta. And then we're just going to immediately find our derivative, du. And we're going to end up substituting that in. That's going to allow us to do our integral. And then we will have to substitute back when we are done. Okay, so getting into the first example then, this looks a lot like what we had before. However, the big thing that you're going to notice then is that our function is identical for u both on the top and the bottom. So that's how I know that this is going to have to be solved in a different way than what we did a few weeks ago. So what I'm going to do, because I see that this here is in the form a squared minus u squared, and in fact, more specifically, it's 3 squared minus x squared. Then I know that I'm going to make a u substitution, or in this case, I'm going to set it x equals just because we're starting with an x. X equals, and remember from before, it was a sine theta. And then for dx, that was going to be just the derivative of this. So we get 3 cosine theta d theta. So our substitution is going to be a little bit different than what we've done in the past. Normally, what we've done is this part here in green has been the part that we take out of the integral, and usually the part on the left side is the one that's going in. But in this case, we're actually doing the opposite. The part on the left is the one that is going to be taken out, and the part that is on the right is going to be going in. So it is a little different than what we've done in the past. Okay, now we're going to go ahead and do our substitution. So we're going to get, integral, and up on the top, we get 3 sine theta, and all of that is going to be squared. Down at the bottom, we're going to get 9 minus, and then same thing, 3 sine theta squared. I'll rewrite sine so it's a little better. Now, one thing that we have to remember as well, we still have to substitute for that dx, and dx is supposed to be 3 cosine theta d theta. So I'm going to multiply that at the end as well. Okay, and what we're going to do now is we're going to start doing a lot of simplifying. So we're going to get 9 sine squared on top. Down at the bottom, 9 minus 9 sine squared theta. And then we still got the part here at the end. Just so you're aware, I'm not going to bother with moving any constants out in front yet, because I see that there's going to be some simplifying. We're going to be able to cancel some of those constants, so I'm just going to choose to keep them inside the integral. Okay, then the next part is we can start, or I should say continue simplifying that bottom. I'm going to factor out the 9s. And that leaves us with a nice thing down there at the bottom, 1 minus sine squared. And so then we can change that 1 minus sine squared into, I'm going to get rid of that page 4 that's just kind of sitting there. We can take that and turn that into cosine squared. And now you should be able to see that this square root down at the bottom is going to be able to cancel with the 3 cosine theta that we have at the end. Now, one thing I want to point out, the Thomas book gets really picky. In my opinion, they include an absolute value on that 3 cosine theta. Technically, that is necessary. I'm not going to require you to do that just because I don't think it's that big of a deal, honestly. So if you want to put the absolute value there, you can. If you choose not to, no big deal either. But as I said, now you're going to notice that those two are going to cancel, and we're going to be left now with 9 sine squared. So there's no more canceling that could possibly happen in this integral. So this is the step now where I am going to take that 9 and I'm going to move it outside. So now 9 integral of sine squared theta d theta. And this integral here is one that I told you needed to have memorized several months ago. What we need to do, either you know exactly how to integrate sine squared, or you know that there is a substitution that has to be done. So we have 9, and then does anybody remember what the substitution looks like for that?
Is this the one where it's like 1 minus cosine of 2ax? Is it this one over 2?
Exactly. Thanks, James. So this will turn into, and actually, yeah, we were using this one yesterday. I completely forgot about that. So 1 minus cosine 2 theta all over 2 dx. I'm going to take this 2 and I'm going to move it out as well. So now we're going to get 9/2 in front. And then that leaves us with 1 minus cosine 2 theta. Oh, and I shouldn't have dx. It should be d theta. Miriam, that's not $1.
It is. Stop cheating.
Okay, so now we can integrate this. We're going to get 9/2. Be careful. When I was originally making my notes, I started switching things to x, and it wasn't just that dx. I actually said the integral of 1 was going to be x. We have to be careful. The integral of 1 right now is actually going to give us theta. So theta minus, and then this is going to be sine of 2 theta. And we have to undo the chain rule, so we got to divide by 2. Plus c. Now, remember that at the beginning of this problem, we started with everything in terms of x, and our answer also needs to have everything in terms of x. Well, although we've got this here, which is going to help us, we're eventually going to have to make a right triangle. A problem that we have is this sine of 2 theta. There's nothing I can do with that. So instead, what I need to do is I have to come up with another substitution. And sine of 2 theta happens to be the same thing as 2 sine theta cosine theta. This was something, the double angle formula, this was something that was covered back in IM3. We haven't used it very often for calculus, though. So now that we know that, we can just change the numerator into that. We can see that our 2's are going to cancel. I promise you we're almost done.
Wait, Mr. Brice, can you make it just a little bit smaller so I can see everything?
Yeah.
Thank you.
Yeah, you're welcome. Okay, and then we'll use that one. So I made a comment earlier about how we are going to need a reference triangle. That's the terminology that the Thomas book uses. So we're going to make a right triangle. And the parts of my right triangle are going to be determined by this x equals 3 sine theta. What we're going to do, we're going to rewrite this, and we're going to turn it into x over 3 equals sine theta. I'm going to move it down just a little bit. And this right here allows me to start determining the sides of my triangle. Because remember from SOHCAHTOA, sine is opposite over hypotenuse. So that means then that here is x, and our hypotenuse is 3. And then we can solve for the other side. And here's the nice thing. This is why we chose x equals 3 sine theta in the first place. The last side of the triangle ends up being the exact same as the denominator in the original integral. And you can see that from Pythagorean theorem anyway, that it indeed is going to be 9 minus x squared inside of a square root. Okay, so I'm looking at this right here. And I'm going to use the reference triangle to help me determine how to make my substitutions. I see that I need a sine theta. That is already done. It's going to be x over 3. I need a cosine of theta. I haven't found that yet. So cosine of theta, according to this, is adjacent over hypotenuse. So that's 9 minus x squared over 3. And the last thing that I need is some sort of expression for theta. And typically what we're going to do is we're just going to use our initial substitution to help us find theta. I know that you could use this as well. You could use the cosine equation, but we're going to use the sine one. And part of the reason too is because that's just a simpler equation. So we might as well try to, it's kind of funny that I'm saying it now. We're going to try to keep it simple if possible. I can admit all of this does not really look that simple right now. So I'm going to go back to the sine equation. I'm going to give myself a little bit more room here. And what we're going to do is we're just going to do the arc sine of both sides. So theta ends up being arc sine of x over 3. And finally, we have all the substitutions necessary to get to our final answer. And it's going to end up being 9/2 times theta is right there, arc sine of x over 3. Then it was minus, and then we need sine times cosine. Here's my sine equation. Here's my cosine equation. So it's x over 3 times the square root of 9 minus x squared over 3 and plus c. I have good news. This is the longest question for the notes today. The other two that I'm going to show you are going to be shorter. All right, is it okay for me to move on?
Just a minute, please.
Yeah, no problem.
All right, I'm good.
Okay.
Thanks.
By the way, in case you all, I know I'm recording this as well. I know I've got the completed notes, but all the questions I'm choosing are from the Thomas book, and it's their example problems, so they'll show you how to do all the work as well if you happen to want to look in your Thomas book too. Okay, so the next one that we have, the next substitution is going to be whenever you have to add two values squared in a square root. And so that one we know is going to look like tangent. Because remember when we integrated before, we knew that integrals like this typically became arctangent. So that's going to be our substitution then. We'll use a tangent theta. And then that tells us that our du, the derivative, well, the derivative of tangent is secant squared. So that's how we get that second part then. And as I told you, I promise that this question will be a lot faster. I would say this one has about half as much work as the last one. Okay, so for the next one, this is the first example of this section for the Thomas book. So again, looking at the denominator, I know that I'm wanting that to be in the form a squared plus u squared. And more specifically, it is 2 squared plus x quantity squared. So then I know, okay, there's my a, there's my u. So based off of the equation I just showed you, what we're going to do is we're going to have x equals a tangent of theta which is 2 tan theta. Sorry. So then the derivative becomes 2 secant squared theta d theta. No, not that one. Let's go purple. Okay, so now we're going to start making our substitutions. So up at the top, we have just dx. So that can just be replaced by 2 secant squared theta. And then on the bottom, we still have the square root of 4. And then it's going to be times 2 tangent theta squared. And just like what we were doing yesterday, we're just going to keep, or yesterday, geez, what we did in the last problem, we're going to continue simplifying the square root, and hopefully we can get a Pythagorean identity used here. So we're going to get 4 plus 4 tangent squared. I'm going to go ahead and factor the 4 out. And like I was hoping, we are going to be able to use one of the Pythagorean identities. Because I see that 1 plus tangent squared, whoops, that's too big. 1 plus tangent squared is going to be substituted by secant squared. So we're going to get some nice simplifying here. And in fact, what's going to happen is that we're going to be able to cancel a secant on top and bottom, and we're also going to be able to get rid of the 2's. So we will end up getting an integral that is just secant of theta.
Wait, Mr. Briss, so 1 plus tangent square theta, it's secant square theta?
Yes.
Then correct it.
Huh?
Then correct it. You got a 2 secant, just 2 secants.
Oh, I did the square root at the bottom.
Oh, yes, I forgot.
That's all right. It's very early. That means $1 fewer.
No, that's not how it works, Mr. Briss.
Or maybe I should have said $1 less $. Ugh, whatever. Okay. Now the good news is that this here is very easy to integrate. We just on the first slide saw that this is going to become natural log of secant plus tangent. And for this question, we are going to need a reference triangle as well. We're going to go back to the original substitution that we made, and we're going to use that to help us create our triangle. And so what I see then is if we take x equals 2 tangent theta, and I solve for tangent of theta, well, that's going to be x over 2. So I know then that I've got my opposite and my adjacent sides. One thing I probably should have mentioned earlier, but I just remembered now. some of you may be wondering, like, how can I look at this and just know that it was going to be tangent as my original substitution? And I'm going to give you an explanation that isn't just because I said so, due to that slide there. No, the actual reason is because this square root, think of when you do the Pythagorean theorem, how a square root appears. Well, in this case, we have two sides added together. And the only way in the Pythagorean theorem that we can get a side that has two parts added together is if that's on the hypotenuse. So what I could have done at the very beginning is I could have made my right triangle and I could have just said, okay, this is all I know. And then I could look at the two missing sides and then think from SOHCAHTOA, well, which of the trig functions needs an opposite and adjacent? Oh, well, that's tangent. And so that was another way that I could have figured out that we start with tangent at the beginning. Maybe what I can do is for the last example, I can start with a triangle, and that might help some of you see why or how we're able to determine our substitution at the beginning. Okay. Anyway, we do know, though, from this equation, though, that we've got x as the opposite side and 2 as the adjacent. And what I see is, well, we need a tangent. We've already got that. But in our answer, we also need a secant. So we have to figure out what that is. Secant is the reciprocal of cosine. So what we need is hypotenuse over adjacent. And now that I have those, I can finish natural log of, secant is going to be square root of 4 plus x squared over 2. And then we have plus, and then our tangent was there, x over 2. And then plus c. So I'll give you all a little bit of time then if you need to write that down. All right, can I move on? Sounds like it. Okay. So the last one that we are going to get into. So this one, whenever we see something written like that, that means that we are going to integrate using secant, or substitute with secant, I should say, and then we'll integrate that. And then we know that our derivative is secant theta tangent theta. So what I was trying to comment earlier about with our triangles, if we look at this, if we're supposed to have something minus something else, when we think of Pythagorean theorem, and if I have A, B, and C, and I think of how can I get something minus something else in a square root, well, normally we have A squared plus B squared equals C squared. If I subtract one of the sides, and then I do the square root of everything, you can see that this square root down here looks very similar to the square root there. Now, obviously my A is in a different place, but otherwise they look very similar to each other. So what I know is that for this one, whatever that part is, that has to be the hypotenuse. And this part here, it has to be one of the sides. And in case you're wondering, how come we chose secant rather than something like cosecant? Well, remember that cosecant, its derivative ends up with a negative. We would rather keep everything positive if possible. So this is a little bit of help to understand why we are going to use secant then as our substitution.
Mr. Bruce?
Yeah.
What was like the U oh my god. What was like the U for what was the U for like a squared minus x squared? What was that one? Like
Oh, that was sine. There it is.
it was okay. Okay.
Okay. So our last example, this one is going to end up being about the same amount of work as the last question. However, there is one thing that's going to make this a little trickier for us, and it is that the fact that now we have a 25 in there. So there's a couple different ways that we can tackle this. Let me know if this ends up being really confusing, because then I can just switch over to the other way instead. So we know that we need to have this as u squared minus a squared. And in this case, what we have is 5x quantity squared minus 2 squared. So for my substitution, if this is the u and this is the a, then instead of doing a u equals, you've noticed that we've been doing x equals the whole time, but I'm choosing to instead start with 5x equals. And according to this, remember u is whatever was squared at the beginning of our square root, and we need it to be a secant theta. So we know that 5x is going to be equal to 2 secant theta. But we want to get this into a form that we're a little more familiar with, which was having it as an x equals. So I'm going to take that. And if we solve for x, well, then we're going to get 2/5 secant theta. Then the other part is that we're going to find the derivative of this here, which is 5 dx equals 2 secant theta tangent theta, d theta. And if we solve for dx, then we know that we've got 2/5 secant tangent. And actually, now that I'm looking at this, I think these second parts probably aren't even necessary, because here's what I'm going to do. I'm going to put x's. I don't think we need those, actually. Here's the reason why. If we come back over to this left side, I've got this 5 dx. Well, we could always just multiply 5 into the integral, which means then that we need 1/5 outside. So we can actually completely avoid, sorry about that, I believe we can completely avoid having to worry about those two parts there. So when we rewrite our integral, we'll have 1/5 on the top is 2 secant tangent. Down on the bottom, we know that 5x is equal to 2 secant theta. So I'm going to rewrite that 2 secant theta quantity squared minus 4. And now this will become just like the last two examples that we've done as well. We're going to simplify that square root, and then hopefully we can make some sort of, use some sort of Pythagorean identity, and then we can cancel something on the top. Oh, I'm sorry. I put in a secant squared there, and I shouldn't have. There we go. Okay, so down at the bottom there, you see that I have been able to simplify that, and now the inside is only secant theta. So again, this will be just like our last example, where we're just integrating secant. So there we go. We get 1/5 times the natural log of secant plus tangent. So like the other examples, we need to make a reference triangle. And so from that first equation, that first substitution that we made, like we've done before, what we want to do is we want to be able to get the secant theta all by itself. So I'm going to take the 5x equals 2 secant theta. And I'm going to rewrite that then as 5 over 2. Or actually, I'm sorry, 5x over 2, just to make it a little easier. I know 5 over 2x is the same thing, but because it is going to be hypotenuse over adjacent, that makes it a little simpler for us. And then, as I've told you before, the missing part in our triangle is always going to be the denominator. But we can figure this out from Pythagorean theorem as well on our triangle. We still need tangent as well for our substitution. And from this, opposite over adjacent. Over 2. And we are finally done. 1/5 times the natural log of secant was 5x over 2. And tangent was the square root over 2. Oh, geez, sorry. And then plus c. So that was the last one. Just barely squeezed it in with 2 minutes to spare. So for the assignment, there's only 3 questions. It's just one of each because, as you can see, these are pretty time consuming. What I would highly encourage you to do, though, is just pay attention to the square roots and think of back when we did the inverse trig functions, and because they are similar, so that will help remind you. Otherwise, use the idea that I had with the Pythagorean theorem here, make your triangle and just think, how can I get a square root that looks similar to what I've started with, and that will help you figure out which of the trig functions to use as well. So there's the assignment. It's only 3 questions, so I'm not going to remove anything, just because I want you to practice one of each. So that is everything. Have a good day, everybody.
Thank you.
Thank you, Mr. Bruce.
Get your mock KPs in too. I've only had 3 people finish the whole thing. Actually, 4 now. But
Bye, Mr. Bruce.
bye.
Thank you. Bye, Mr. Bruce.
You're welcome. Have a good day.